Okay, you're going to pick it up now. As I told you, we're going to deal with this amazing story of migration in the loggerhead turtles. So here's what they are. Loggerhead, I guess I should say sea turtles. And this animal is pretty amazing. Some of you guys might have had the great opportunity to see them. I'll try to throw a little video clip in to show some of their biology. They're amazing animals, especially with the beginning of their lives. I'm going to tell you a story that a lot of you might not be aware of. So the work is generated from a couple of very prolific scientists. So Dr. Kathy and Dr. Kenneth Lohman are their names. You can find these guys at UNC, so that's University of North Carolina, Chapel Hill. And they have a really nice website that pretty much presents in a very accessible way all of their research findings from their lab. And I would like you to go there to kind of embellish your notes. And I should be able to give more information on that when we meet again after spring break. But for now, if you look these guys up, you can't go wrong. You can find some really cool things. So the loggerhead turtle here's the Latin name, Caretta caretta. And I'm going to give you a little bit of basic biological information so we can kind of set up what they do for a living. It's the most abundant U.S. sea turtle. So in U.S. waters. And it is, like a lot of these animals on the threatened list, it happens in all but the most frigid waters. And frigid is going to be important to us a little bit later on. Frigid waters for these guys spell trouble, that's for sure. So there's a dimorphism here, certainly a sexual dimorphism based on size. The size variations, males of this animal can be upwards of about 3 feet in length, and their weight is 250 pounds. Females can be a lot larger. Females can get upwards to 1,000 pounds. So what do they do for a living? They're carnivores. Their food is pretty highly variable. They're going to be jellyfish, conchs, crabs, fish, and occasional seaweed. Jellyfish, conch, crab, even fish. So that's what they do for a living. And the cool thing, behaviorally, is that the females come back to their natal beaches. So put that on the board. So females of this loggerhead return to lay their eggs when they're adults to their hatchling beach. To call it they do what we call oviposit. We've seen this before, and oviposition is a very awkward thing. They actually swim to the shore, and then they start to lumber up the slope of the sand and eventually get to a good place to dig a hole. And if you've ever seen this, it's pretty amazing. You can't interfere. You're violating federal law and international law if you interfere with any sea turtles laying their eggs. But interference is something that's probably changed in definition through the years. You definitely can go up to them and watch them in their pattern. Of course, that should make you think of central pattern generators and just a routine behavior. But she makes a lot of noise when she's ovipositing. It's kind of like, these big bellowing, kind of panting sounds. It just looks like an incredible amount of work. You don't want to shine bright white flashlights on them, but you can approach them maybe with red lights. So I've been told. I've seen it once with a group of my students in Florida. is a pretty amazing phenomenon. And some of you may have seen it. Some of you actually may even want to take it one step further and get involved, because there's a tremendous number of people that volunteer to basically assess sea turtle oviposition in nest sites. I mean, it involves routine kinds of walks on the beach at the right time of night. It involves going out the following morning and maybe seeing the evidence. You can see these tracks very easily. And they even construct little fences, or at least put signs where the nests are, to make sure that visitors to beaches don't mess with them or set up their picnic site right on top of a nest. So it's a pretty cool thing. Great conservation biology, really. So anyway, back to this female. It's going to return to their nesting beach. What we want to really talk about is return from what? It's the first chunk of their lives that's going to be very interesting to us, and is going to represent this incredibly complicated navigational and migrational pattern. All right, so here's kind of therefore what's going to happen. Oviposition is going to be basically in the sand, and it's going to be basically below. It's going to be in a hole. And when they hatch, these hatchlings are going to have to do some behaviors. Hatchlings of these turtles are first going to have to dig out. That's the first thing that they do. Now I want to think about this in terms of what we just went through. What is digging out? You better know which way to dig. Digging down, digging up, and of course that comes down to gravity. So I want to suggest to you that we have a geotaxis. As a matter of fact, let's put a positive or negative to that. Is digging up and out, away from gravity, a positive or a negative? So this is a negative geotaxis. Nice. Negative geotaxis, that's going to get them out to the surface. And then they have to find the sea. And there's a good bit of work by the Lomans that talks about the stimuli involved with finding the sea. So this is primarily is primary visual. So I guess what we should say here is a phototaxis, if you will, or even a telotaxis, if you will. So they're going to find the sea, and they've done a lot of studies to see if other stimuli are involved in finding the sea. Of course, at night the sea is an amazing display of light. Moonlight bouncing off of the waves. But there's also a lot of sound, isn't there? And then the other thing that you should think about is that if here's the sea, and actually close in on the sea there's crashing surf, and then here's the beach, like so, and then down here is our nest. So the nest is subterranean. Turtles gonna dig out of the nest. That's step one, and then they're gonna find the sea if everything goes well. Another curious idea here is this is down the slope of the beach. So all of a sudden you could kind of have almost a positive geotaxis. We all know how to go downhill. I mean, we feel it. And they've looked at some of these various features, like the sound of crashing waves, like the negative geotaxis of going down the hill, but it really seems that the visual modality rules supreme here, and that's what they do. So they're going to go, and then once they get into the water, a whole bunch of other things are going to happen. So if you go to the Loman site, you're going to see that this is a very tumultuous and crazy thing. You've got all of these currents that are taking place here with the waves. We call them the undertow, and it's important for these animals to be able to bust through these waves to get into the open ocean. So that's what I'm going to call here, open ocean, and this is where they really need to get. So let's finish this little flow chart. They find the sea. I've already said it's primarily visual. Let's see what else they do. Once they find the sea, they have to navigate. Here's another word we just learned. Navigate the wave zone. And that's what I'm talking about right that's kind of what I'm talking about right here, this wave zone. Very important for the animals to get somewhere. And then the next thing is that they're going to have to orient in open water. In the open ocean, in the absence of visual cues. This, my friends, is migratory. And it is not a seasonal migration, it is a multi-year migration. Most of these animals in their migration defines their juvenile life. Juvenile, of course, means pre-adult, and adult means that you have functional gonads and you're ready to mate and get the business done. And this thing, the typical, most stay several years in the open ocean. And the distance traveled is about, well, it can be as many as 9,000 miles traveled through their lives. They do return, so this is this whole migration phase. So I guess I'm continuing my flow chart here. The next thing that they do is they return to their natal beach, or their hatchling beach. They return as juveniles, however. So they're still juveniles, and these are coastal waters, so I should say to coastal waters. And then they reach sexual maturity. So I'll highlight that, and then of course they will oviposit. That's pretty much where we are in their life cycle. So that's what our turtles are going to do. We are going to spend a bunch of very, very detailed, focused time with this phenomenon right here. We'll do a little bit more here, but we're going to really sink our teeth into this migration period in the open ocean. We've got to lay the groundwork for this with some of the important kinds of constructions here. What is the open ocean from the big picture perspective? What is going on? What kinds of stimuli are out there? What could these animals use to actually achieve navigation? So that's where we're going, but one of the things I want to let you know is that this part right here, finding the sea and getting through the wave zone, big star, this must, for many reasons, be a quick phenomenon. They have to get down this slope and through the wave zone very quickly. There's a lot of things to go wrong here. I mean, I don't know if any of you have seen this. The video clip can show a little bit of it, but this can be a bit of a turtle hatchling buffet for a lot of predators. So we've got these animals coming down the slope, these young animals, and it's, you know, you've seen the movies many, many times. You know, it's the late night, you know, Animal Planet Discovery Channel thing, and you always hear real sweet, cute music when they show the little sea turtle, and then it dramatically changes to horrific music because you see a big predator. And these predators are just picking these things up and killing them and eating them. It's pretty brutal, and of course the people that make these films, they add sound effects. It's called the Foley artist. So they're, you know, somebody sits in there and says, well, I wonder what it would sound like if, you know, if a big predatory bird got a hatchling. And so they take a couple of coconut shells or wood blocks or something like that, and they click them together, put these sounds to basically emulate the sounds of nature, and it's just horrific. Crunching, dying sea turtle babies. And then getting through here is really equally difficult, but finally in the open ocean they've made it. And there's always going to be a certain percentage of them that don't make it. I want to tie this into some of your ecology as well. A lot of you remember from at least your Bio 2 classes this concept of kind of ecological strategy. You might remember something like this where you have time and you have N and you have different populations, different kinds of organisms that could actually exhibit exponential growth extremely rapidly because they have what's called a high R value, and then and then other animals that might have a slower R value. So this is a high R, which is rate of reproduction. This is a lower R. And that's the first model. So we call this the exponential model for population growth. Exponential model, population growth. And then you might remember that we have this more realistic version. We thought, you know, populations of animals just can't grow to no end. There's always going to be limitations, competition for resources. So we came up with a model like this, where we introduced a concept called K, which was the carrying capacity. And then we actually defined that as a population beyond which the population couldn't grow, and we made this logistic curve. They called this the logistic model for population growth. So here's N and here's T. N is the population size. And then, based on this particular model, a very important concept was produced where we have the RK continuum. And in the RK continuum, we had this concept of, in the RK continuum, we have this concept of the R strategist. And then over here we had the K strategist. And, whoops. So R and K strategy. And these ones were kind of the weeds of the world. And yes, animals can be weeds, but these are the ones that produced huge numbers of offspring. So large, so I should say something like a high fecundity. So large numbers of offspring, very low degree of parenthood. And then over here on this one, we certainly had low fecundity. So fecundity is the number of offspring. And then we had over here a high degree of parenthood. And there's more things down the line here. I don't want to really just kind of go over what you've done before. But what I want you to do with this information is think about sea turtles on this continuum. And if this continuum is a line from absolute R to absolute K, where on the continuum are loggerheads. Now, why would I want you guys to do this? This is our first conceptual framework for what we really would call ultimate causation for behaviors. You think about this. Parenthood. Well, parenthood is a catch basin of behaviors. The most simple behavior for an animal that's very R strategy is just find a place to lay your eggs and leave them, and leave large numbers of them. And then you don't care about them from that point on. Hint, hint, hint for where the turtles are. And then something like us with an extraordinarily low fecundity. 1, maybe 2 offspring. We only have, as promised, we only have the nourishing material for 2 offspring at any given time. Like you could have twins and you could feed twins for a while until weaning. But it would be more difficult if you had more babies than you had milk for. And then, of course, we have an extraordinary degree of parenthood. I mean, it takes a long, long, long time for our offspring to actually not fend for themselves and be totally fended for by us, totally cared for by us. So this is this continuum, and when we start to talk about ultimate causation, every different animal that we're going to talk about is going to fit somewhere on this continuum. Most of the examples, however, are going to be skewed over to this side, because this is where all the awesome behavior is. Behavioral strategy, you know, things like foraging and foraging for your offspring and coming back and feeding your offspring. So we're really making a nice transition right now in this class, where we still have plenty of proximate, plenty of basic nuts and bolts, nervous system sensors, although we started to actually consider many things at once, not only just one stimulus and the route and the muscular response, but now we're actually putting together complicated behaviors. And we're at the point to start to think about their evolutionary causation. Like, why are those behaviors there? And it's related to survival, it's related to passing on your genes, it's related to natural selection in the big picture. So this is really good stuff. I hope that this rings bells from your past, but if not, I hope I've given you enough information to kind of get hip to it. All right, back to our turtles. So the whole turtle thing is there. And we need to kind of get everything constructed around this to understand the system. So, let's see. Okay. So if there's enough time left on my memory card, I want us to go into the ways with which these turtles navigate in the open ocean. Let me get a new black one. So one thing we need to get under our belt is this. I'm going to tell you right now that navigation of these turtles in the open ocean is going to use the Earth's magnetic field, which I haven't even talked about. The magnetic field, so we're basically going to say some form of magnetoreception. And this is cool stuff, very impressive. There are two variables, and we need to get into these. I want to show you the Earth's magnetic field first. So I want you to construct this. I'm going to take the Earth off of its tilt and make it straight up and down. So I guess technically, therefore, that here's a North Pole and here's a South Pole. It's not a very good circle, but it's as good as I can come up with at this point. And then I'm going to draw very straight across here what we would represent as equator. So there's the equator. Here's the NP, here's the SP. So there's the planet shifted off of its tilt. And now let's draw and extend this outward, and let's draw some lines. So we'll draw a little line like this, and then let's 1, 2, 3. I think I'm going to draw a big one like this first. And I'm going to draw a mirror of that on this side. Okay. In between these lines, I'm going to put 3 more to kind of fill the spaces. So, arrowheads here. Okay, nice. So, this is the Earth's magnetic field. First thing we need to define is something called the angle of inclination. So they're going to actually use, so loggerheads will use 2 things. two parameters, two aspects. So two aspects for navigation of magnetic field. The first of these aspects is called field inclination. So this is basically an angle. Let's see, an angle. And that angle I'm going to show you here. The first thing, at the poles, so right here is the pole. This angle of this field line is coming in at a 90-degree angle. If you were standing on the North Pole, so the surface of the planet is the floor, the field inclination angle is coming straight in. The angle between the surface of the Earth and the field inclination, the magnetic field line, is 90 degrees. So you can all see that, 90 degrees. At the equator, it is actually 0 degrees. So you're standing here, and the line is perfectly parallel to you. So this one is 0 degrees. 90 degrees here, 0 degrees here. So field inclination is 90 degrees at the poles, and it is 0 degrees at the equator. So these turtles are going to have the ability, depending on where they are, north and south here, because it's 90 degrees here too, isn't it? 90 degrees at the poles, 0 degrees at the equator. A turtle that is here is going to be experiencing a different angle of inclination than a turtle that's here, etc. So there's going to be a piece of information for the turtle that is going to give kind of their, north-south kind of direction. That's a coordinate. The next thing that loggerheads are going to use, the second of these, is going to be field intensity. This one's a little bit more weird and not as simple as you would think. But in general, I'm going to say first off that field intensity is variable, but in general, the magnetic field intensity is stronger near the poles and weaker near the equator. Okay, so definitely pay attention to this. What I just said about field intensity is that if I was on the equator, that would be a less intense magnetic field than if I was up here or down here. Stronger near the poles, weaker at the equator. So that's the basic information that that these turtles are going to be able to use with regards to magnetic field. Turtles are reptiles. Other reptiles do this. Some invertebrates can do this, and a plethora of birds can actually respond to and detect the magnetic field. So this is not unique just to the loggerhead sea turtles. There's many animals that use magnetoreception and the various attributes of the Earth's magnetic field. Okay, so how would you go about studying turtles with this kind of crazy world? We can't detect magnetic field. It's very difficult to have some little instrument to do it. But how, as an experimenter, can you vary these things and systematically perform controlled experiments on the orientation or the navigation behavior of turtles? This is intense. I'm going to show you the Lohmann setup, at least conceptually. So this thing's going to start off, like we've already seen. The kiddie pool is a pretty important piece of equipment for behavioral studies. So the Lohmann system, to basically study these things, we're going to first take our all familiar kiddie pool. There's the kiddie pool, and more on this in a minute. But inside of our beautiful kiddie pool, we are going to fill the thing up with water, of course, like so. And this thing will be standing on a really robust platform. So they have this thing suspended on these concrete piers. The reason they're doing that is that the Lohmann system has a couple of devices. It has a box sitting over the top of this. It's made of robust coils. Try to show you that. So that is a particular kind of coil. Actually, it has kickstands that go all the way down to the floor. That. Let's run this thing down like so. So this is a big kind of constructed box called a coil. And this coil is going to be used with voltage to manipulate magnetic field. There's also another coil that's involved here. This one's a lot more difficult to draw. Comes out further. A series of coils kind of projecting backwards. Let's see, I'm going to try to make this as good as I can. So these are also coils. And you don't need to go too crazy with these. But the idea is that we have kind of a series of coils kind of working back. I don't know if that's very good. I suppose that I could circulate the picture. You could definitely see the real instrument on the website, the Lohmann website. So this thing and this thing, I'm just going to call coils, and I'm going to say powered coils to manipulate magnetic field. They can invert the magnetic field. They can switch it. If it was this way, it can go that way. They can route that. They can vary the intensity of the field. So the attributes of the magnetic field that we just talked about can be manipulated with this device. Okay, so kiddie pool, water, time for turtles, right? So here's what happens on the kiddie pool. Inside here, you basically have a device, a centrally kind of anchored device that's a pivot upon which our little turtle is going to be taking a ride. So you have kind of a little, spinning device that has a little leash, and there's a turtle swimming. So here is, I'm going to do a blow up of this so you can see what's going on. But here's a little turtle. This thing allows them to record the direction that a turtle is swimming. So if we took a look at the kiddie pool, we would have kind of an arm that spins. So this thing is capable of spinning, and then at the end of it, a little leash. And at the end of that, you've got your turtle. So here's our beautiful turtle swimming, our little turtle hatchling. And the little turtle has, let's make him cuter than that. The little turtle hatchling has a Velcro vest. And upon that Velcro, this attaches to it. So here you have this turtle that's you know, that's swimming from top view. So this is top view, and you can actually get a directional point. These turtles are amazing. So the first thing they have to do is collect these little tiny turtles, or upwards to larger juveniles. They've used everything from hatchlings in these studies up to pretty sizable turtles, and they're swimming, and there's a certain direction to the swimming. So every trial, a little turtle in a magnetic field will tend to start swimming and stay swimming once it's oriented, once it's settled in a particular direction. It doesn't just keep swimming off in different directions, it fixes, and it swims that way. So the data look like this. Here's what the data are going to be rendered as. We're going to see it always presented as a circle, and of course the circle we could say north, south, east, and west. And how we'll record the data. Every trial is going to get a little circle. So that's one animal, and you'll see, so you might see some turtles exhibiting this from a set of trials. And usually you'll see something, you know, sometimes you'll see some really strange ones, like what the heck was that turtle thinking? It went totally different than most of their counterparts. And the data starts to look something like this. And so what the researchers will do, so keep in mind, every one of these points is one little hatchling turtle that was subjected to a given set of magnetic field conditions, and it was aligning in those and swimming in a direction indicated on this kind of compass face of the data as a spot, as one dot. And if that was a series of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 16, if that was n equals 16 trials, our general direction of the results of this study, our general direction would be, yeah, even though a few of them were off, these turtles were going pretty much in this direction. So we put the arrow to represent kind of the mean direction. The mean direction of the results of the study. So what we're going to see the Lohmanns do in a series of experiments is we're going to see them vary one at a time the different magnetic field attributes. They're going to just deal with angle of inclination and see what that does, keeping everything else constant, and then they're going to deal with field intensity and not vary angle of inclination, and then they're actually going to pull both of those together, concordant cues, and see how that impacts the orientation of these sea turtles. We've got one more crucial piece of information to gel with this, and that is the whole basis of why these animals need to do this, and it's called the Atlantic gyre. When you go out into the open ocean, you are in a giant toilet bowl of current, and that giant toilet bowl of current called the Atlantic gyre is a good place to be. But if you get thrown outside the current and get flushed up to the north, cold, frigid waters, as previously mentioned, bad for turtles, death, predators, freezing, and the same thing happens in the south. So if you're a little sea turtle that's going to go out and spend years out there in the open ocean, you know, developing, eating, growing up, you need to stay in the gyre, and the magnetic field will be key to that. So that's where we're going to pick up with this lecture in a moment. All right, you guys, I'm going to pick up what we were talking about last time. I wanted to show you that this is the stereotypical representation of data from one of the experiments that take place in these kiddie pools. So this isn't any specific result. I just put these spots here on this face, which represents the compass, north, east, south, and west. I just put these spots here to kind of show you how the net result is, it's a 360-degree data set, and you pick kind of the, or you determine the average from these various directions, which is indicated in this particular case by the red arrow. So the little turtle is swimming here, and of course the turtle orients, so it swims ultimately and it settles on a certain direction. So what we're going to see as we move forward with the experiments by Lohmanns is they're going to step by step vary individual aspects of the Earth's magnetic field and see how the turtles respond. And then finally, they'll actually put two different of those magnetic field variables together, and we would predict that that should produce a better and tighter data set, right? So let's see what happens. So I will erase. All right. So we're going to look at an experiment now. And this particular experiment is going to have to do with the ability that demonstrates, or can they demonstrate, the ability to detect detection of field inclination. We just got done talking about field inclination. That was those kind of concentric circles that have the lines of the Earth's magnetic field. And it's 90 degrees at the poles. It's 0 degrees at the equator. So we want to see what can happen with these little tiny turtles in the kiddie pools when we dial in various fields of inclination. So remember, therefore, field inclination, the variable there is going to be angle. And of course, that's going to be in degrees. So, pre-experiment, I want to establish what we do. So we get these little turtles. I'm not too up to date on their collection methods, but of course, it has to be seasonal and they have to get them from the field. And then they're going to take these little tiny hatchlings and put these little Velcro suits on them, and then they're going to be ready to go. The first thing that they're going to do in the apparatus, which of course is the kiddie pool, is they're going to allow these guys to, so the tethered hatchlings are going to be allowed to swim towards a dim light. Now, that's our pre-experiment protocol. This is going to be for all tests. This is kind of just, they're swimming, they're getting used to the thing, and they do tend to orient towards the dim light. So I guess we should point that out. That's kind of neat. What is towards light? You guys, we just learned this. This is obviously a positive phototaxis. Yeah, so that orientation stuff that we just talked about, there we go. This is going to be with us for a long time, these kinds of language. So this is pre-experiment, and then what they'll do to run the experiment after a period of time, this is like an acclimation period, if you will. After a period of time, they'll turn the light off. The light will be turned off, and then they will, as I said, with that big apparatus, they're going to dial in. They're going to dial in the angle or the field intensity, whatever the experiment is. So dial in the angle of inclination. And then, of course, the little turtle, upon experiencing that, will be detecting magnetic field, angle of inclination in this case, and orienting whatever corresponds to this to this setting of degrees. So let's take a look at the results of two experiments. Okay. So the first experiment, experiment 1, they're going to do a 30-degree angle of inclination. So here's the results of 30 degrees. So again, This is the data set. So north, east, south, and west representation in terms of which way that the little hatchling was swimming at the end of this. And here's what the data looked like. They're surprisingly kind of all over the place. You even had some that went in the wrong direction, I guess you could say. But you did start to see some kind of lining up more towards this sector than anything else with angle of inclination. Again, you can see some in different places. I don't think it's too important, you know, that you're dead on with this, but if you came up with a mean response for this particular data set, this was your mean. So that's where these turtles lined up, is that they were swimming to the northeast. So for 30 degrees, the result was, and again, it wasn't tight in general. in general, they were they swim to the northeast. I should let you know that the little dim light that was on beforehand was due east. So most of these turtles kind of shifted a bit to the left after they turned off the conditioning light, and then they went for the total magnetic field. So that's what we see with the 30-degree angle of inclination. Let's now take a look at what happens if you dial in 60 degrees. All right, so then experiment 2, I probably better put color on this so you guys can. So experiment 2 here is going to be a 60-degree angle of inclination. Now I want you to think about what you remember about that. What's happening to the angle? At 0 degrees, it's 0 degrees at the equator, and it's increasing to 90 degrees at the poles. So the first one that we had, 30 degrees, was going to be at some latitude. 60 degrees would actually be further north or further south from that, depending on where they are. And if you remember that, that's closer to danger, possibly. So let's take a look at 60-degree angle of inclination result. The data, again, pretty much all over the place, but in general, we see a lot more of these little turtles kind of orienting down here towards the bottom. So every one of these, one data point, one final direction that a little hatchling kind of latched onto, and this is kind of what this data set looks like. You might even have one way back here that was totally off. Of course, you know, this is bell curve, survival of the fittest, right? So we see this result, and most of them are going down this direction. We put this line right here. So at 60 degrees angle of inclination, we see, as a result, that they're generally swimming to the southwest. So that's pretty cool. All right, so that's only using the angle of inclination as a variable. Of course, in the real world, there's going to be 2 variables present. The next set of experiments, we're just going to look at responses to the field intensity. And I got to give you a little background on this. Okay. So this is our next line of experiments. So I guess I would say experiments to determine if they can detect or detection of field intensity. All right, field intensity, that's another thing. We're going to start to draw maps to show you what this looks like. So here's going to be my crude attempt to kind of draw North America, Gulf of Mexico, and some of this cool stuff, and South America. Wow, okay. That's what it is. That's what I'm giving you. So there's South America. and we only need to focus on this part. So this is my poor attempt to draw a map. Here is going to be some of this stuff over here. Let's see. I need, wow, I don't know if this is very good or not, but hopefully it will work for you. Okay, Africa, South America, North America, Europe. So let's throw a couple of islands up here somehow, some way. Wow, that didn't go very well. So this thing kind of goes off like this. So we got some of this stuff going on. We got some of this stuff going on. I don't know how good that is. Let's go that way. So with this in mind, I'm going to be able to draw the gyre. So I guess I've tried to draw this once before. So this is the Gulf of Mexico. So here's what we see with the gyre. This is this big gyroscopic current. It's kind of this big gyrating toilet bowl current, basically, that is in operation. Of course, some of this travels through the Gulf, so we get this happening. And then this big swoop up here is our Gulf Stream, and some of that actually goes all the way up here to the British Isles. So that's going to be our depiction of the Atlantic gyre. This, as I mentioned before, is where our turtles, our little turtles, spend their juvenile years. And then they'll come back home. And of course, we're monitoring populations that, as adults, reside on the eastern coast of the United States, right here. So we're looking at the life of a juvenile turtle in here. Of course, I've also defined that if they make a mistake and they get swept up here, this leads to cool water, bad places, predators, etc., exposure, death. And I think there might be a similar phenomenon down here. But right now we're going to focus just on this. The next thing I want to do is show you the field intensity phenomenon. So we're going to dial in reference point 1 for our experiment right here. So I'm going to erase that and put in the letter A here, and I hope that you can see that. So that's our first experimental point, and I'm going to give you some of this information in a minute. The next one is this particular point right here that was dialed in, and that is B. Okay, so this particular point is going to be for an experiment. This is an intensity called, that's dialed in of 52,000 nanotesla. So this is the measurement units for field intensity. 52,000, this is a pretty big number. This one's a little bit lower. This particular number here, dialed in, was 43,000 nanotesla. So nanotesla, those are the units. So this one we're going to call experiment 1, where they dial in 52,000 nanotesla. Again, they're not including the other aspect which we just described, which was angle of inclination. This one is going to be focused on field intensity, and we're going to compare this one versus this one. So here's experiment 2, 43,000 nanotesla dialed in for this experiment. Remember, just like we described before, that the start of the experiment is dim light to the east, and the little Velcro jacketed hatchlings are swimming by phototaxis towards the east, turn off the light, dial in the nanotesla, and then these guys will swim until they pretty much end up in a steady direction. And that direction will result in a dot, a data point, on this 360-degree field. I'm not going to show you the individual data points here. I'm just going to draw the results of this experiment. This is a slightly smaller set then, MSW. So here's the direction that these guys responded. Dialed in here. That was the direction. This experiment, a lower amount, a lower degree, produced this result. So, different intensities. This is a really cool diagram for us to take a peek at, because you can see that if this is the direction that they're swimming, they're pretty much swimming with the gyre, and they're certainly swimming in a way to be in the gyre. And at this particular case, they're kind of swimming in. Better that they're swimming in than perhaps, actually some of them do go off here for a Mediterranean vacation. This right here, ultimate destination for awesomeness. Hancock's favorite place in the world, or at least one of them. So, I haven't been to many places, but boom. Okay, so these guys are swimming in a way that at least kind of keeps them in the gyre. We don't have the whole picture though, because we don't have both variables. We don't have angle of inclination and field intensity at the same time. The last thing I want to do though is use this map to show you that there's a bit of funkiness to the field intensity. If you took a look at the way field intensity operates on a map like this, of course the equator's way down here, what we want to do is kind of show that it's not perfectly parallel to the equator like latitudinal lines. This thing is going to be kind of creeping around. These lines kind of creep. So in general, it gets stronger towards the poles, but what I'm trying to draw here with these lines here is to show you that this is actually quite a bit lower at 43,000 nanotesla, but it doesn't look like it is on the map. And this is a pretty decent map. I mean, I'm sure my country outlines are pretty bad, but it looks pretty good to me overall. And I wanted just to make the point with this orange pen then that the field intensity in general gets stronger towards the poles, but as you can see, this thing kind of is, it's a bit waves. It's wave-like. So it's not a straight line. It's not straight latitudinal. All right. So there we go. I'm going to leave this awesome picture of the gyre up and move to the next experiment. You guys can redraw it if you want, or you can go back to it. I think you might want to redraw it, but I have the luxury of being able to take out the stuff I don't want, and I'll leave it here. So this ends the field intensity experiments. Now we're going to do the double experiments. So I'm taking out a bunch of stuff here. I'll repair it. So you guys might just start drawing a new one if you want. That would be best. So you guys should redraw this thing. I'm just going to try to salvage what I have so it looks the same. It's hard for me to draw quality maps in succession, so I'm going to go with the one I have because I'm happy with it. Okay. Take out my field intensity lines. Take out my south of France lines. Excellent. Okay. So I'll erase the title. And let's get this business underway. Okay, I'm going to repair. There we go. All right. compare a couple of the gyre lines so everything looks nice. Of course, I'll have to erase again in a second. Okay, so there we have Africa. Okay, so there we have our gyre in place. Let's take a look at the next experiment. And what we're going to call this experiment, this is the big one. This is kind of the combined. So this experiment here has to deal with using what's called regional field. And regional fields. And the regional fields would be defined for us as the combination of angle of inclination and field intensity. So that's what this is. Regional fields is equal to the combination of the angle of inclination and the field intensity. So we can use both of these things. And I'm just going to put some locations. So the first location is going to be the same as we had before. So here's going to be A. I'll change to a green pen so it stands out. Here's A. And then location B is going to be pretty similar to the last location that we did. Here's B. And then we're going to do one all the way down here. This is going to be location C. So there's our locations now for comparison. This means that we're going to need 3 graphs to show this. So this guy right here is going to be experiment 1. And I'm not giving you any numbers to show what it is, but this of course would be a combination of a certain angle plus a certain field intensity in nanoteslas. This one's probably 53,000. So let's take a look at that, and then we're going to look at this data with this one. We're going to call this experiment 2. Oh, this is experiment 3. I'm going clockwise. And then this one right here is going to be what we call experiment 2, and that one's dialed in with the 2 variables. Here's what experiment 1 produced with the turtles. This guy, they were going in this particular direction. Now, I don't have the actual data, but I want to just show you an example of the data. I'll use green. This is not actual data, but it represents it. And you basically see a much tighter rendition of swimming direction in these animals. And not too many are making a lot of mistakes. These guys were showing, with both pieces of information, they're a lot tighter. This is a lot tighter of data set, and it shows that, hey, we're using 2 things here, and they're both helping for the orientation process. Boom, boom. This is super important, so I'll put an exclamation point, concordant cues. So you're using 2 different aspects of the magnetic field. They're both contributing in a positive way. So this is concordant cues. And then there's something else I'm going to say about that in a minute in this little piece of board. So that is experiment 1. Experiment 2 shows this particular degree or directionality, pretty much due south from this point. That makes perfect sense as well. Look at that. Experiment 3, you guys can guess which way are they going? Perfect. Look at how these data show that the orientation of these animals with no light would be bad to use, just using these 2 aspects of the Earth's magnetic field, keep them swimming in a direction that allows them to stay in the gyre. And they're going to stay in the gyre for years, as I mentioned. So this is basically a fundamental survival instinct that keeps them in a good place to grow up. Lots of food, not so much danger. This is their world. And it's all about the Earth's magnetic field. Okay, so we go to the angle of inclination and field intensity as concordant cues. The other thing I want to mention is that another way to look at this is that this is an example of what we call mapping. To map something, you got to have two pieces of information. So, you know, if I said that, let's see, where are we here? 38, 39 or something latitude, and if I said that was my location, that would particularly be a line around the entire globe that didn't give any, it just gave that one particular general coordinate. You need two coordinates for a map. Both of these combined together produce coordinates. So, boom. This is mapping. Mapping is demonstrated here. And of course, as I was just trying to tell you, mapping requires at least two coordinates. So we have two coordinates here. Coordinate 1, coordinate 2. Mapping has been demonstrated. It's pretty amazing. You think about how far that we have come in understanding how animals do what they do from this proximate basis. Well, look at the big time ultimate significance here. What is the ultimate causation of this entire behavioral framework? From its proximate underpinnings to the practicality of keeping these animals, they stay alive. And these animals pass on their genes because they go back home to their natal beach and they mate and they go in and they produce eggs, the successful ones. The ones that were haywire in this regard and perhaps swim a little bit too northeasternly during during this leg of the gyre got swept up and probably became killer whale prey. That's how it works. Ultimate causation, proximate causation, boom. A wonderful kind of union here. We're right at the crossroads. This is cool stuff. So that is the last thing that I'm going to say about the sea turtle story. At least I think so. I'm going to double check my notes. Yes. Aha! No, more to say. That's where we're going to go. Okay, so there is all I have to say about the sea turtles. And I think at this point, that's enough for us to basically carry into the week after spring break. So that is what I have. And take notes on this stuff just as I did. This is intended to basically be a full, truthful replacement of lecture. So in other words, my expectations of you with this material from the sea turtle lecture and the orientation lecture that preceded it is just as if you were sitting in my classroom taking notes. It's kind of cool though, because you can go back and forth and perfect your notes. If you guys have any details that need to be worked out about this, you can get into some other information. Okay, so now we're going to move on. How would you do a navigation study with birds? Wow, that gets a lot more difficult. Some of you might be thinking, oh yeah, I remember. Those guys flew those ultralight planes. But of course, they were the leaders. They had conditioned little tiny waterfowl to grow up and fly with them. It was pretty amazing stuff, but what about birds that are doing this radical north to south migration, seasonal migration? My favorite cliff swallows, I keep talking about them. We'll talk more intensively about them here in the near future, but those guys are probably starting to make their way up now. They're making plans from South America to get up here. They should be arriving while we were actually still engaged in this semester. And you can see them, you know, building their nests and things over the river. So But how do we study bird orientation? This is pretty tough. It's kind of limited. You don't study them in flight. That's pretty difficult unless we get to the point of setting up these very incredible little devices. And I think that this is in the works. I'm not on top of it. I'm not a field ornithologist that studies migratory patterns, but little chips, little things that can actually engage with satellite communications, and we can follow individual birds. I think that is happening, but until then, we go back to the 20th century and we see how they did it. It was pretty crazy. Birds, so we deal with, we know that their migration is seasonal, and so we set up a device that is kind of like this. Here's the arena, and of course you've got, you can't let your bird fly out, and there's a little bird hanging out down here. This is a pretty poor drawing of it. So here's our bird. Wow, looks like a kingfisher, doesn't it? Let's make him impressive. Okay, so here's our bird that's in this funnel. And then what we do to this funnel is we coat this funnel with this black ink wax paper. It used to call it carbon copy paper. And as a matter of fact, back in the day, again, this is in the 20th century, but I had to make carbon copies of my chemistry lab data. So I'd have to stick this piece of paper in between the page that I was writing on in my lab book and then another white page underneath. And it's kind of like your checkbook, if you have that kind of a checkbook where you have a record that automatically records what you wrote the check out to. So this is this idea, it's a funnel. So the funnel assay is what you do, and what you need to do with the funnel assay, of course, is the seasonal conditions for your animals have to be the same. We are about ready to segue into the seasonal aspects, what we call biological clocks. So we know that in any given time of year that a migratory bird is either going to be close or approaching a northbound flight of migration, or as the clock continues, as the months continue, ultimately a southbound flight. And these migratory flights are going to start with them taking off. Well, if you do that, these birds take off in a particular direction. So if we take this thing and project it to its 360, it looks like this: north, east, south, and west. So here's the top view of the funnel. And we've got this paper. The bird takes off in its migratory direction, and it leaves scratch marks because it can't get out. So it keeps flying and scratch, 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 scratch. Poor little bird, right? Yeah. So you end up with all these scratch marks in one particular area, and it's usually pretty much in one direction, and that shows that, hey, wherever this bird was, it was taking off to the north. And so think about our birds here. What time of year do you think that this was? That's a question for you to answer. This is a data set, north, east, south, west. What time of year was this for these birds to take off? Some good thinking for you, because I'm not telling you. Okay, so that's the funnel assay for birds. We see that. There are other things that we can do with direct observations. For instance, scuba divers have seen these migrations of spiny sea urchin, or spiny lobsters, which is an impressive animal in the Atlantic and Caribbean. You'll see these guys kind of going in almost like a funeral processional. Well, hopefully not funeral. Some of them do get eaten. But anyway, they're going off in one particular direction. Spiny lobsters are another well-known example of organisms using magnetic cues for their orientation. So there's a number of animals that do it. Let's take a closer look at magnetic compasses, or things that, manifestations of magnetic detection. This is a very elusive area of science, surprisingly. We just can't get in there and open this black box. So we have circumstantial evidence that indicates the location of magnetic detection structures. And I'm going to take you through some of that right now to kind of close this topic, and then we'll get ready for when I come back. Okay. All righty. So the concept now is we're gonna really have more on, and I'm gonna put this in quotations, compasses. So we're talking about a compass. That's the word that we use. If you guys need a device that tells you the direction of north or where you are in relation to the Earth's magnetic field, it's called a compass. So that's what we're gonna call these anatomical features, or biological compasses. So maybe we should throw that in. Biocompasses, and that's what we're going to do. Matter of fact, we should call them biological geomagnetic compasses. Biological geomagnetic compasses. So this is kind of a black box, as I mentioned. You know, the kinds of experiments that we can do is find out what structures are involved, because, you know, you can take certain kinds of animals and cut something out and it doesn't function, or destroy something and it doesn't function. Some of these brutal experiments that are easier these days to do with invertebrates than they are certainly with vertebrates. So it's kind of a black box. We're going to look at these three kinds of ways that have been proposed to describe these biological geomagnetic compasses. Actually, it's really two ways, but there's two subtypes, so it's two major ways. Two major ways. So the first of these major ways is what we call magnetite. Small particles of a substance called magnetite. Magnetite in the upper beaks. So this is going to be a bird deal, upper beaks. And this has been documented in pigeons, for instance. Small particles of magnetite in the upper beaks. Remember too, for instance, if I said pigeons, like a famous pigeon, a homing pigeon, I described homing behavior in a previous lecture, and that's kind of a really super short term but frequent migration. And that again is going to require north and south mapping, possibly other spatial learning components such as your landscape. But I think of passenger pigeons in that particular thing. Small particles of magnetite in the upper beaks, that's the first one. Makes sense. The next one, I guess I should say a little bit more about this. So magnetite is a substance, ferromagnetic, that is going to align. These particles will align in a magnetic field, relevant to that magnetic field. And therefore, there's going to be certainly a directional concept with how they align. So, next thing, magnetoreception. This is the second major category, magnetoreception using special photoreceptors. Okay, photoreceptors, that is going to pull us in a little bit, and there's two of these. So again, for my number 2 and number 3, they're really subtypes of special photoreceptors. The first one focuses on macromolecules. Macromolecules. So these are big, huge molecules that are going to not, in this particular case, be light responsive. We've talked about photoreceptors and big macromolecules like pigments. You remember a small discussion on rhodopsin, which is a substance that when light impinges on it, it changes its bond angle. We're talking about macromolecules here that align in magnetic field, but it requires something to happen. So here's the idea. You basically have this macromolecule. Here's a macromolecule, and you're going to have singlet macromolecules, singlet state. macromolecules. So they're only individual. When they get impinged upon by photons, here's my photons, come on. I hope you guys can see that. Photons, I need to come up with a better orange. So photons, theoretical particles of light, impinge upon our singlet state, and this is going to cause an excitation, and that excitation is going to cause these things to exhibit a triplet state. So light hits them, they become in the triplet state. This thing is capable of aligning in the magnetic field. So that is one proposed idea. So the idea of photons, photoreactive substances producing a magnetoreactive substance, basically. So photoreactive becomes magnetoreactive is kind of a way to look at it. That's the first sub one under these specialized photoreceptors. The next one, which is my third, so 1, 2, 3. The next one is small free-moving ferromagnetic. Small. Let me write it down. Free-moving ferromagnetic crystals. Ferromagnetic crystals associated with light-absorbing molecules. In oil droplets. And these align parallel to the magnetic vector. Okay, this is not over, but I'm running out of room down here. So the rest of the story is when these line up in a certain way, they impact the amount of light impinging upon the photoreceptor. That's the crazy coolness of this. So I'll try to squeeze this in the bottom. So this alignment right here, let's see, this alignment of all these molecules, it modulates, depending on how intense it is, modulates, or the direction, modulates the amount of light reaching the photoreceptor itself. So that's pretty complicated. That's the whole deal right there. That's pretty complicated. And again, these are best ideas. This is what we think is going on, or what they think is going on. Suppose I should tell you a little bit about magnetoreception in different animals. So here's kind of a brief survey. not every animal system is going to be studied, and the first thing you have to do is just have that tiny subset of animals that utilize magnetoreception. I mean, think back to my mosquito. Do you think they have any purpose for magnetoreception? No. They're governed by the other things, predominantly chemoreception, photoreception. So magnetoreception in animals, let's take a look at this. The first section that I want to provide for you is appears to be dependent on light. And here's a few of the animal systems. Newts are studied, and birds are studied. Of course, birds are going to show up everywhere. Birds and fruit flies. And by the way, we're going to dive into fruit flies here in another capacity. Fruit flies are almost off the list, just like white rats. White rats and fruit flies, and then that little worm we talked about way at the beginning of class called C. elegans. They're almost not animals anymore. They are so studied, perhaps so overstudied, that I almost want to kick them out of the kingdom. They're almost fictitious. They're almost constructs of empirical data. They're no longer really animals. Although I think you could probably all leave some rotting fruit in your trash can and collect some Drosophila melanogaster, the real ones, if you wanted. Anyway, so fruit flies are funky, but guess what? They've been studied in this capacity as well, and that's that. So it appears to be dependent on light. The next category appears to be light independent magnetoreception. So let's see, double lines here, double lines here. And let me give you this list. Mole rats. Wow, if you've never seen a picture of a mole rat or even been to one of the zoos that have them in the world, they're pretty funky. God, it could almost be, you know, there's certain bucket list kinds of animals, and I would be I'd be less interested in seeing the big animals of the African savanna. I'd be more interested in seeing those funky ones with all sorts of interesting sociality or degrees of it, like mole rats, or of course anything in the weasel family. That would be cool. So there's reasons to go to Africa, even if you don't like lions, tigers, and big ungulates. So mole rats, the next one, sea turtles. These are our guys. We just did them. And the last one, the all-familiar mealworm beetle, which some of you would know that as food for your herbs. So there's a few standard systems with which magnetoreception has been studied, and in certain cases light is crucial. That gives particular insight for you to kind of relate to number 2 here, doesn't it? Dependent on light, and then systems that appear to be independent of light. So there we have it. That closes the book on all of this magnetoreception stuff, and now we're ready. This is what you should be entirely through by the time that I show up on the Monday after the first week of spring break. So have fun.